Barry Barish, welcome
Hi.
back to the Into the Impossible podcast. It's your third time on the show. Thank you so much for doing this.
Hi, Brian. Good.
You're one of our audience's most favorite guests for many reasons, and very special to me, and influence on my life and career, and actually the progenitor in some sense of my second book called Into the Impossible. Think Like a Nobel Prize winner, which you did honor me by writing the foreword to that book, the second book. And since you've been on the show, the first time in 2020, when the kind of inciting incident that we'll get to led to the creation of this book, I've added a new feature to my episodes where I ask authors of books to help me and the audience judge their books by their covers. Which
by the covers.
Yeah. You're never supposed to do that, right? You don't judge a book by it. But what else do you have to go on, right? There's almost no information, especially if it's somebody that's a relatively unknown author. So an author spent a lot of time ruminating about what to call the book and so forth. But I thought we'd play we play that same game, even though you didn't write this book, but your name is on the front. So when we talked first, it was actually the second or third time we had ever met, we spoke about this notion that it's very common in science called the imposter syndrome. And I remember, clearly as day, and I told my wife that I just couldn't believe that we closed out the interview when I asked you, as I asked all my guests as well, what advice you'd give to your former self. And you basically said, to kind of get over the imposter syndrome. And I often think I'm not good enough to have the imposter syndrome. But but I was blown away. And I said, Barry, you won the Nobel Prize. And you said you still have it. Maybe you could recount a little bit of that sentiment that you expressed originally.
Well, I think anybody, if they actually think about it, has it. I happen to have a psychoanalyst for a wife, so I can't avoid kind of the self-reflection that makes it maybe more evident than otherwise. But no matter what, I think anybody is in company where people are have more ability at whatever you're talking about than you do. And I don't remember what I said in the early one, but the image that comes to my mind was actually at the office of the Foundation for the Nobel Prize. Did I talk about that?
Yeah, that's what I'd like. Yeah, I'd love to share that
that
story,
was the. So I'll just repeat it in a few seconds. And that was, you go and, there's all this excitement, everything makes you feel like you're 10 feet tall through a week of celebration for the Nobel Prize. And at the end, you go to collect your check and sign the book and get your the portrait that they use as the official portrait in the foundation offices, which aren't very, fancy or anything. It's just a set of offices in a nondescript building in Stockholm. And so you go through all this stuff. They take your picture and so forth. And eventually they say, oh, but you also have to sign this book. And they pull out this little book. It's nondescript. It's more nondescript than yours. It doesn't, as I remember, it didn't have much of a cover. Maybe it's a leather cover.
Couldn't do this segment.
And they opened to a page that had nothing on it because of the fact that in Nobel's will, physics is first, so physics is the first one to get it, and probably the first one in the office. And my name starts with B, so I must have been the first one. They opened this book to a blank page, and the top said 2017. And they just said, sign your name. It's okay. I signed my name, and then I didn't know what to do, so I paged backwards. And then you see the names of all the people you idolized in your life, Einstein, Feynman, blah, blah, blah. And if that isn't a moment when you feel like you don't belong, which is kind of the dramatization of this syndrome, then, something's wrong with you, I think. So I think it's a feature that we all have and should just be aware of it. It shouldn't stop you from anything. It's true that you should be aware that you're not uniquely, because nobody is better than everybody else in the world at everything in the world. So the fact that you can do some things better than others and other things better, and that you have some real perspective on yourself shouldn't make you feel like an inferior person. But I think everybody should have, or else they're unaware of it, some semblance of this syndrome. So.
Yeah, I always find it tough to strike balances in life between, extremes. It's always so easy to fall into extremes, and that's why there's so much polarization in politics and even in science. But to kind of go down that middle road of being humble on one hand, as you say, but also, you need to have a little bit of swagger to feel that you can accomplish something that we set out to do as scientists, because it's so ambitious, right? I mean,
I think you need a lot of swagger. Having swagger is not orthogonal or to having some sense inside yourself of your own limitations and your own self not being better than everybody at everything. It's just, I don't think those are contradictory at all. I think to accomplish something, you need to have a spirit of gambling, you need to have a spirit of adventure, you need to have a swagger, and you need to be willing to fail. And probably that fourth one's the most important.
The other revealing thing that you kind of struck me with, like a thunderbolt, the first couple times we spoke, was this notion of curiosity being the driving factor. Yeah. And you highlighted something which I had, kind of glossed over, whatever, that there are all these negative associations with curiosity.
Yeah.
Can you speak, why do you think that is? If it's such a valued component of the, and unique to human experience, why is it sort of spoken of in cautionary terms?
That's really a good question. I don't have, my wife would have a better answer.
Right.
I think it's probably somewhat psychological.
Right.
I think it has to do with us trying to, from a young age, have structure and feeling how important it is for kids to have structure, but yet kids are adventurous. So I think probably the time period that I picked on, because it's what I think is more or less where it's dramatic, is a kid that gets to be capable of doing a lot, maybe a preteen kid, a kid between 5 and 12, where the kid has a lot of natural curiosity, is very adventurous, is hard to contain, and yet we have parents who try to discipline them, and then schools who put them in a cage. And curiosity and following curiosity fits into this, adventurous spirit that a young kid has. I think it's really to try to feel we have to make kids grow up and have structure. And unfortunately, that's true for parts of growing up, but it's got to be tempered in ways, and somehow having enough sophistication to let kids pursue curiosity while they maybe don't, wreck something in the house or other things that you control them is an art that parents need to be better at. And especially schools where we really do emphasize the discipline and basically kill the curiosity. And that to me is something, fortunately for me, I avoided, and that it could easily have happened to me as others. It just happened, I escaped and still have that. And probably you did and certain others, but I think a lot of adults have basically limited themselves because the discipline of the system, schools could be changed, and parents have limited them in their way of approaching.
And also, you mentioned the word art. There's an art to parenting. There's an art to being a graduate student advisor. There's an art to being, a teacher, a TA of undergraduates, if you are a graduate student. I guess the thing, I've studied, kind of meta-scientific, people that study the habits of scientists, the sociology of scientists, which you remarked on at one point with in our conversations. But I guess the question I have is, I think it was Merton or somebody like him who said, like if Einstein didn't come up with relativity, someone else would have. Whereas, the Mona Lisa, if it wasn't painted, as it was, it wouldn't have just spontaneously come about in exactly the same way. Maybe something of equal beauty. I mean, you could say the Scream, or who knows. But do you think it's possible to teach, art? Let's say as an artist. I don't know that I believe you can teach someone who has no ability to be an artist. Like I have no ability to play music. I can hardly play Spotify on my phone, right? And I don't think I could be taught to play music. But I know I was taught to be a physicist by mentors and folks like you, and I endeavor to do that with myself. Do you think that science and art are different cultures, as you know, Lewis or others used to call it, are fundamentally, can you teach someone to be a curious, imaginative, scientific thinker who may not innately be predisposed in that direction?
Oh, I thought you were going to compare with artists. To teach people to be curious?
Yeah.
Oh, I don't. I think it's innate. I think we're all curious. So it's hard for me to say that it's something we have to teach. It's something that we have to support and something that we have to let grow and thrive. I think it's built into, that's why all kids, they are adventurous. I really don't think the big problem is somehow teaching kids how to be curious. I think it's somehow stimulating them to be curious in an effective and positive way.
Mm-hmm. When I think back about, you know, kind of the things that drive me in my career now, I seem to be much more kind of unifocused on exploring the cosmic microwave background and finding it, you know, kind of all-consuming. And when I look at you, you were obviously at many points in your life focused on a single project, but how did you have the discipline, the sense, the kind of, you know, confidence to pivot, as you did several times in your career, to make outstanding and tremendous contributions? Is there a point when you realize it's time for me to make a change? When I spoke to Ray Weiss, I'll just say, your colleague and fellow Nobel Laureate from LIGO, and he said when it stops being fun.
Yeah.
Would you agree with that?
Well, that's a piece of it. I think as a scientist, theorists are good at it because there's not much overhead. What I mean, good at changing, okay? They can go throw it in the wastebasket and take on another problem, and what have they lost? Not very much. So somebody could have stimulated them. For us, there's more of a balance. You've got a big investment in something. And I think it's maybe a little more like an artist. When do they finish a painting and move on to the next one? There's no defined way to define when a painting is done. And when you look at the variety of paintings, some are very sketchy, some are very, very detailed.
Warhol said, in fact, you know, great art is never finished, it's just abandoned.
Yeah, okay.
Stop
and I think Picasso was very, very good and articulate about the fact that you have to let it be. You've done it, it's done, you move on. And somehow, for experimentalists, we have a big investment, like somebody that did a very detailed painting. And there is an art, I don't think you can learn to do it, an art to know when you're done as yourself and when to move on and how to move on and where to move on. And somehow it's something I've kind of developed, but it had maybe was not a complicated thing, maybe because of my personality. I'm not really set where I do something in a particular way and have to get to some end, but you also don't want to quit something too early. I don't know, as a experimental physicist, I think it's maybe a little bit like I criticize grade school teachers. I think we are pretty bad in our education. And the course that I teach here at Riverside and we'll teach at Stony Brook next fall is aimed at a problem that I've always felt was there, and that is in graduate school. In fact, it was the reason why I started doing this teaching. In graduate school, we're very good at teaching theorists about physics, and then they go out in the world and they're very good at crumpling paper, the good ones, and moving on to another problem. Experimental graduate students, we tend to, it's hard. You have to learn techniques, and you have to do a lot of very hard, boring work in a laboratory, and then you have to do something that's publishable and blah, blah, blah. And so graduate students come into UCSD or here or wherever, and they have taken courses in a lot of things, and then they start to go to work for somebody. And as they proceed through graduate school, they become narrower and narrower, but deeper at what they're doing, and narrower and narrower. And it's very common too common for a graduate student to get their degree and basically continue on the same track. I contend that there's nothing fundamental that restricts experimentalists from moving from one area to another. Mm-hmm. I mean, I've done it not because there's something very special about me, any more than theorists. There's more of an overhead. You can't crumple a paper. You have investment that may have equipment and money and so forth. So it's got to be somewhat more deliberate. But I think still, as a research scientist, you should be doing not something because you have equipment or you have knowledge in a particular area, but because it's going to move science forward the most. Mm. And so at some point, a different science problem than you've been working on may be more a better way in terms of a product to invest your time, energy, and effort. Mm-hmm. And I think there's overhead in doing it, but it's never been one that's constrained me. Mm. I mean, the overhead mostly is the system. You know, a university hires people in certain areas. When you go into another area, it screws up their bookkeeping, kind of. They don't like that. You have built a certain trust and ability to get funding by a certain funding agency, but it's not just the funding agency, it's a subpart that does the field that you're doing. So when you switch, you have to, but these are all, you were able to get funding the first time, you were able to convince your physics department of what you did the first time. So the fact that you change is it's never been a big issue, I think. And I think it also, to be honest with you, it keeps you young, it keeps you going to change and do other things. So to me, it's not it's a natural way to do things, and we don't do a good job of creating products that have that mentality. Mm.
And you use the word product, but I guess I would say, what is the obligation of the student? Obviously we feel a lot, you're a product of the University of California system, UC Berkeley, we'll maybe get to that later on. But what are the responsibilities of a student? Let me ask it specifically. What is the bare minimum that an experimental student, grad student, what should he or she know about theory? And what is the obligation of a theoretical graduate student to, specializing in theoretical astrophysics or theoretical physics? What should he or she know about experimental physics? What are the obligations on the student?
Is the right word obligations, or the best way to be an effective scientist?
That's the latter.
So let me just change to be effective. Mm-hmm. I think, like all these questions, if you take the extremes, there's no real answer. If you take theorists that are very mathematically oriented in their contribution to physics, maybe in moving the fundamental theoretical tools and ideas forward, maybe don't need to really understand much about interferometry and how LIGO works, or about a CMB experiment, right. Other than what the acronym means or something. And on the other hand, very, very technical experimental students maybe don't need to understand anything about string theory. And so I think it's really the body of us that are more in between. Any theorist that is doing theory that might be testable, so not string theory, which so far isn't testable, but experiments that it's testable, is a better theorist if they have some sense what is testable when they do it, what it takes to be testable, and maybe they're more enriched also by understanding how experiment validates theory, or maybe leads theory in some cases because of what they found. And then we can go the reverse, and that is experimentalists, unless they're totally technologists, they're developing, the next laser for LIGO or something, are better off even if they're developing the fancy optics that we need in the upgrade that we're presently doing to LIGO. The what's going to come out of that is better sensitivity to see further out in the universe, and some sense of what that will enable, I think, is enriching. It should go beyond that. It shouldn't just be
More is better.
no, it shouldn't just be what's the product of your own research. You know that.
I see. Yeah.
But maybe be as a trained experimental physicist to be able to appreciate, if they're working in LIGO, to be able to appreciate CMB and so forth, because it's basically understandable and so forth. So as a scientist, I think at some level to be able to understand and communicate and know that enables them to not be then, in order to be practicing, it's fine to be in LIGO and be an experimentalist that is the theory, but to not have your eyes open broader means you're again following this path that maybe you shouldn't be on your whole life.
Yeah. Yeah, and I definitely think there are aspects of the experimental method that can be useful to a theorist, trying ideas, doing thought experiments. Obviously, Einstein didn't spend much time in the lab. He has a few patents, as you know, but he didn't spend much time. But he is master and is extremely well known for the Gedanken thought experiments. And thinking about those and what Popper called decisive experiments and how they could not prove a theory but falsify it, right? And so you mentioned string theory, and I can't help but kind of pivot on this expertise that you've gleaned over your career in classical gravity, and wondering, because we've never talked about it, what are your perspectives on the possibility, the probability that we'll ever have a quantum theory of gravity?
That's a really good question, and I wish I knew the answer, but I'll just tell you my belief right now. I'm old enough, I've watched 50 years or something of people, theorists, trying to bring these two fields together. It's been a very strong, maybe slightly fringe because they haven't made progress, but there's the attempts to do quantum gravity has been going on for 50 years and basically haven't succeeded.
Right.
Okay. So my sense is that like other areas of physics, what's the problem is that they're working in a vacuum, if you want. They're working without the clues that you need to actually find your way. That in physics we need some sort of clues. And the problem is that most of the physics that we do, the forefront physics now, is very deep, very good, but it's absolutely in one area or the other. Right. Whether it's gravitational waves, where we're doing general relativity, and maybe we'll see some violations of Einstein's general relativity, and that'll give us some clue. But so far we haven't, but we're doing something that's pursuing general relativity. And if you go to CERN, they're basically looking at the shortest and shortest distances, which is where quantum field theory is the king and does things. We need to find somewhere where you need both the science that general relativity is trying to describe and the science that quantum field theory or quantum physics at short distances is trying to define. We don't have that at the present time, but I could imagine places past our lifetimes maybe. And one is the very early universe. So the very early universe needs to be able to explain both, how we made particles, why there's more particles than antiparticles, and all the relativistic effects that happen in the very early universe. So if we could really explore the early universe, maybe someday with gravitational waves or some other way, but the true early universe, that would be a laboratory where you have to satisfy both things. The same is true of black holes. So if we could actually study the physics inside of black holes, which we can't do now, you have to preserve all the quantum numbers, all the things that we treasure in quantum physics, and you have to obey the rules of general relativity. We have to find a laboratory where both things are satisfied and then get the clues, I think, to do this. Unfortunately, I don't know of anything right now that we're close to being able to do that. And so the experimentalists are failing to provide the information that would give us the ability to bring it together. So it's not just that theorists are failing because I think they're failing not because of the lack of tools, they have different ideas, but to a large extent because they don't have the experimental hints or clues or things that they have to
boundary
have
conditions.
to use. And I can imagine there are places. I gave 2 examples, but maybe there's other places. But what we have to find is places where you need both together, and that's hard because one tends to work at very short distances, the other at long distances and high velocity. So.
When I can't resist asking you this question. So you're an experimentalist. You're known for tremendous contribution in many fields, but most recently with LIGO and the study of black holes. Let's say you reach that biblical age of 120. You've accomplished everything. You're about to enter the promised land, which for you would be these accomplishments. I want to ask you, if you had a one-way ticket to visit a black hole, would you take it? At 120, so you've got many, many years. You should live and be well, but you're about to reach that age. You got a letter from God saying your time is up. Do you take that trip?
No.
Why not?
I don't personalize the science that I do enough to do that. There's things I'd like to do before I died. But it wouldn't be to go to a black hole. Would you?
I would. If I had lived that long a lifetime and gotten to that advanced age, Moses didn't get into the promised land, and this is my opportunity. I would to want to understand what it's like. And by the way, you wouldn't feel any pain. I've got another letter from God that says you wouldn't feel any pain, spaghettification, or as my 4-year-old calls it, pasta-sized. But to see it and to experience, and this brings up, I had this opportunity to speak to a philosopher of science recently from Rice University, and we had a great conversation. But at the end of it, I was left really with kind of an existential crisis, because essentially everything that he said and that I mostly agreed with, it's all perception. Even an experimental dial will read something that's just a translation into a voltage or an amplitude, and so we never directly experience sensations or the true reality. We have proxies, and I guess the ultimate kind of removal of those is experiential. As you said, you're not emotional. Maybe I'm more emotional, and so I would like to see it because in a certain sense, there's that experiential opportunity. Obviously, this is not likely to happen. Disney's not likely to make Journey to a Black Hole anytime soon in reality. But this notion, I want to ask you, do you ever? I felt exasperated by talking to this wonderful man, brilliant professor, but the sense that there is almost no reality because everything is an interpretation of electrical signals that we perceive through our sensors that get processed through other chemical nodes in this fat and cellular-based computer on our shoulders. And I got very exasperated by it because it basically said you can't really experience anything, it's, or that all experience is almost illusory. And so I feel like our job as experimentalists is to make, as Galileo said, measure what's measurable and make measurable what is not yet so. But do you ever feel like what we're doing is only an approximation of reality, or do things like that not really trouble you?
Well, I can relate to it, but I think we're a little different.
Yeah.
In that what I would say is that maybe I'm going to say the wrong thing, but that you personalize your science much more than I do. Well, if I want to go to a black hole, why don't I do it instrumentally? And I wish it would happen during my 120 years that we can actually get inside of a black hole and do what we're talking about. But I would feel very satisfied by the fact that we built an instrument that could do it or had developed the techniques. Not that I personally was transported in so I could look and see. So I haven't, I maybe I'm a little jealous of you, actually, that I think it's a nice feature to be able to personalize what you do with yourself. And I think you have I think it's a good thing. You have the feature that you are personalizing in that image and probably in personality in the science you do more than I do. And I kind of wish I did. It would be more fun.
Well, it's one thing you can
I mean, as my colleague said, you should have fun.
Yeah.
And that's what science is about. And I think it's hard to have fun if you don't personalize. So I think you have a capability you could exploit.
Kind of inspired.
But it can be frustrated, but trying to have fun is frustrating sometimes too. So you do things. So it's got the human emotions. I think I detach my human emotions more from my science than you do probably. And I don't know that that's a good thing. It's a personality.
Yeah, it's a personality thing to be sure. I was really prompted by that experience that a friend of mine, Peter Diamandis, who's a medical doctor, a futurist, and so author, and he was the medical doctor who certified Stephen Hawking to take the zero gravity flight. And in the flight, Stephen's face was, purposely contorted because he couldn't really smile in this way, and floating around in zero gravity was just this highlight. He and Eric Vieri is at UC San Diego as well. They coordinated this trip for him, and it just made me think, like, if he was that pleased flying on a DC-9 or whatever it was, all the more so flying on Kip Thorne's interstellar traveling device to some black hole or something like that. But pivoting now back to Earth, I always find that people are fascinated with their origin stories, and so to speak. And you are a product of the University of California. I wonder if we could briefly recapitulate the kind of early exposure that you had as a young student at Cal, and how that maybe has carried lessons that maybe or maybe not still exist to this day with the way that you teach and mentor and practice science. Yeah.
So just to say, I didn't really get interested in science until almost end of high school. I thought I was going to be a writer. I think I said that. But so I came from parents that didn't go to college, so I had a little guidance. And I decided I had to do something, so I applied to engineering schools. Those were UCLA. For me, it was the public education system, and it was either UCLA or Berkeley. Those were the two schools at the time, and you had to take an exam to go in engineering, and I chose Berkeley. I got into both, and I went to Berkeley, and I took usual freshman courses, and I didn't particularly respond to engineering, which I'll forget for now, but I did respond, it turns out, to the fact that I had freshman physics, where I was exposed, at least secondarily, because it was a freshman physics course, which is kind of boring things, to the fact that they were discovering a lot of new particles and so forth up at the radiation lab. And in particular, the instructor I had was Owen Chamberlain, who got the Nobel Prize for discovering the antiproton. He had discovered the antiproton before I was a student, but didn't yet have the Nobel Prize at that point. And it was really the inspiration of him, who I never got to know really well. It's just, I was a young student, but it was looking at Owen Chamberlain that inspired me to at least change fields into physics. And again, it was through him that I got into research, even though he did nothing for me in research. I was a very good student, so I didn't I had extra time, and he suggested I get into some research, which was uncommon in those days. Now we push our students to get into research as undergrads. And so I signed up for some research units with Chamberlain, and he was at the radiation laboratory, which was a hike up the hill. And now there's a shuttle bus that goes back and forth.
Easy.
But
in
then
my
there
day,
was a hike up
both
the
ways,
hill. Yeah, and I'd go up the hill, and on, I don't know, Wednesday afternoons or something, when I was supposed to do my research units, and he was too busy for me, which was nothing to do with me, but there was a big overhead in going up the hill, so I'd wander around, and the big accelerator at that time was the Bevatron. You could go anywhere almost then. They didn't have as much radiation safety things. But the Bevatron was kind of inhibiting for me, and a young kid wandering around. And I wandered up to the other cyclotrons and so forth. met people, learned how to do all that stuff, and that's kind of what captured me. It was open, it was fun, and it was all a new world.
Yeah. Nowadays, you not only can't go wandering through the cyclotrons, but even the chemistry sets you get for your kids have, baking soda and vinegar and no radium like they did when I was a kid.
Yeah.
We've really neutered a lot of what the exposure that kids get to explore their curiosity. Safety is sort of trumped exploration, but there are good aspects of it. Our mutual friend Gary Sanders talks about people that would go into the beam line and they would look to see inside the cyclone, see if the beam is operating with their eyes, and thank God those things don't happen anymore. But when we look at the University of California, obviously this is produced in part with the UCTV, the best production studios in the world, and we have the best students, I feel, on the planet as well. Looking back, you said what advice you'd give to yourself regarding kind of your psychological perspective in a previous show, but I want to ask now, scientifically, you're starting grad school, take you back to Berkeley, back when you started grad school. Is there something else that you would be fascinated with if you were starting off today? A lot of the low-hanging fruit, we never have a term for high-hanging fruit. I don't know what it is, but I feel like my son asked me recently, what's science going to be like in 2050? Mm-hmm. And I felt like, which will be maybe the final question, we'll talk about artificial intelligence and computer-aided physics, but we'll get to that in a moment. But I sort of suggested that maybe it'll be just as ambitious, but the discoveries might be smaller in a certain sense. I don't know if you agree with that, but what would you do now as an incoming grad student at Cal or a young student at Cal? What would you be studying? What would you be fascinated by?
Let me start with physics and then maybe go broader.
Yeah, of course.
So first, how is it different to be a grad student in physics like I was compared to now? And how might you approach it differently? When I was a grad student, I think I was really fortunate to be in a place where they had developed all these world-leading facilities that I could learn about and be part of. But actually doing something was different than now. So so they're so great. There was a facility. They were able to do new things, but I had to learn how to be a physicist and do physics. At that point, it really, when I was a student, you had to conceive of and build new instrumentation, like you're doing for your thing, but as a grad student. I mean, basically, that's what you did as a young student. You basically had to build something that somebody hadn't, to build electronics that would be faster, to do something, to be able to do something somebody hadn't done. I think that's not the problem facing an experimental student today. I think it's just almost flipped, and that is that the problem was physics at that time was ahead of instrumentation, and so you had to build new instrumentation, and then the physics followed new instrumentation. Before me was things like a bubble chamber. When I was there, we were just creating the electronics to do accurate time of flight. The particles would go along, you do accurate time of flight, and then you could tell the difference between a pi meson and a k meson or a proton, because the heavier ones went slower. Mm-hmm. And you could distinguish them by doing time of flight, and you had to make fast electronics to do that. But you couldn't go buy it, you had to build it. And so the idea was there and you build it. Today, I think the problem is different. If you think of the technology that you need to improve an experiment for CERN, the calorimetry, or LIGO, or other things, not the big ones that are very, very engineered, but anything else. There's the wealth of techniques and technology that hasn't yet been applied to physics. So I think the cleverest and most successful students of today that will stand out in the ways that, say, I've been fortunate to stand out, will have the ability to be the first to use techniques that have been developed elsewhere. I don't care whether we talk about machine learning, which is underused in physics and astronomy compared to other things, for a reason that we use statistics to do our analysis to determine what's right or wrong, and statistics and machine learning are kind of orthogonal because it's a black box. But machine learning can do things very well. So how to apply machine learning to help you, or developed electronics or other things. The outside world has developed faster than we've developed. I remember when silicon detectors were first developed for particle physics detectors, and they're the most precise way to track a particle, and that's basically using something that makes microelectronics that you do on, and the first ones were used in particle physics. They had the limitation they weren't radiation hard, so you put them around a beam and they wouldn't last very long. And the early experiments, even the ones done at Fermilab, had a lot of trouble employing these tracking detectors, which were 10 times more accurate than the tracking detectors where you have individual wires and so forth. And the first time it ever was done accurately enough was developed by particle physicists, and they discovered the top. And the discovery of the top at Fermilab was the last experiment done on an accelerator, not because the accelerator got better. It was because they had developed the technology of silicon, which couldn't be done earlier. Now the outside world is 100 times better at silicon than we are.
Yeah.
And so there's a lot of places where the technology has moved in the outside to be better. So it seems to me if I were a young starting graduate student now, I would learn as much as I could about technology and how I can answer questions now that people couldn't a decade ago because of the technological advances. So I think the table's turned in a sense for experimental students.
So I said that maybe for the final set of questions, we hear a lot about artificial intelligence, machine learning you mentioned, but they're distinct. But there's been not a small amount of discussion about whether or not you could make an artificially intelligent physicist, basically to explore data sets or to actually divine the laws of physics and even retrodict laws that we already know about and maybe predict new laws that we don't have yet knowledge on. I want to ask you this quote from Einstein. You're the man who gave you imposter syndrome later on in life, despite winning a Nobel Prize and many other accolades. He said, do you remember he said that the happiest thought of his life was that an observer in free fall would experience no gravitational field. And he called that the happiest thought. Now, and I always say to people that make these claims, like my friend Max Tegmark and others, that we're going to have artificial AI, Einstein. How can a computer, first of all, really replicate that? Because it wouldn't have a sensation of free fall, because it doesn't have the visceral sensation, A. And then B, what would happiness mean to it? Now, maybe a computer would have some other metric that it could optimize that we could call happiness, but it seems to me what led Einstein to the equivalence principle in the form that he used to derive the laws of general relativity that you employed with your colleagues. Are you sanguine about that? Do you feel like there will be artificial Einsteins and Kip Thornes and so forth, or do you think that there'll be aids like we use, to go shopping and to, find the best thing to watch on Netflix or UCTV? I can only talk about what I call the finite future, what I can see and what I can't. I think AI can't do what Einstein was talking about, or an element of what we all do, and that is that as good as the fact that it's getting great at playing chess, Go, analyzing data if it's the right, if you have the right kind of data, better than us at synthesizing a lot of data faster and so forth. It basically has made no progress at all in reasoning. And reasoning is the word I would use. In reasoning, it seems to me, decision-making and reasoning, which is not made from doing an analysis of facts but comes from somewhere else, is the heart of what
creates these other emotions. It's the fact that he reasoned what it was like to be in an elevator is what then gave him the emotion of happiness. But the fact is, the reasoning that he did, could you duplicate that? Not the happiness,
Right.
but the reasoning itself. And there's no progress in that at all. AI doesn't do that.
Right.
And so I think as long as, and I don't envision how it can, it's something that's in our brains that humans have that we haven't made any progress in being able to replicate or understand. We have an ability to, I mean, you can't capture it in one word, but the word I would use is reasoning, not happiness is an emotion. So, no, I don't think so. I think we're unique as our brains someday will maybe understand what consciousness is and what something like reasoning is, how we make decisions based on not just an analytical thing, and choices and so forth is a very human element that's basically not something that scientists, whether physicists or anybody else, really understands. And so I don't see it duplicated.
Well, it's good to know we'll have job security as physicists. That.
But as I said, that's through our vision, how long we can see, but that's probably through our lifetimes anyway.
I appreciate your tremendous vision, Barry, as usual, being so generous with your time and with your inspiration and mentorship, not just to me, but to millions around the world. And I wish you many, many years until I can convince you to come along on the trip to the black hole's event horizon.
Yeah.
That'll be for another time. Thank you so much,
right.
Barry.
Okay, thank you. It's fun.